Today we want to continue the study of objects that are under the influence of central forces. Today we have a very interesting example that is named as the Isotropic Harmonic Oscillator. Okay, actually, well, the first characteristic of this harmonic oscillator is that, well, the potential energy that describes this kind of motion, well, it will be described with this expression that we have here. The potential energy in the harmonic oscillator will be 1 over 2 times m times omega squared r squared, where omega is, well, the angular frequency of the motion. Okay? So remember that, well, in this case we are going to have here the reference system and a vector r that is pointing to the object. Okay? And this object, it has a potential energy determined by this expression that we have here. So in this case, this will be an example of an object that is under the influence of a central force. Another thing is that, well, we saw on a previous video named as the equation of the orbit generated by a central force. Well, in that video we found these two equations that we have here. Okay, and well, these equations allow us to determine, for example, the dependence theta of a function theta of r, okay, where theta is this angle here and r is obviously the magnitude of this vector that is pointing to the object. Okay, so we can find a relation between theta and r if we are able to solve this integral that we have here. Okay, and well, with this other integral we can determine a relation r of t that will tell us what is the value of the magnitude of this vector, okay, on a certain time t. Okay, for example, we will have another value of r here for a different value of time. So we need to solve these two integrals to know, well, these two very important relations, in this case for the isotropic harmonic oscillator. Another thing is that on another video we showed that the general Lagrangian of a particle can be expressed in polar coordinates with this expression that we have here. It's not very hard to show that, well, this is the general Lagrangian in polar coordinates. Okay? Another very interesting thing is that, well, to find the total energy of the particle, we just need to sum the potential, to switch this minus for a plus in the Lagrangian to get the total energy. Okay? So other thing is that, looking that there are no external forces, this total energy will be a constant. Okay, so for example, what happens if we take the Lagrange equations for this Lagrangian over here? First of all, we see that the derivative of the Lagrangian with respect to theta, well, it will be 0, okay, because this Lagrangian does not depend on theta. That means that the derivative with respect to time of the partial of L with respect to theta dot, it will be 0, making that dL d theta dot will be a constant. Okay, so if we calculate that, we are going to get that, well, it will be m r squared theta dot, and we will name this as L. The reason that we named this quantity as L is that, well, it will have something to do with the angular momentum. So we express the angular momentum with the letter L. Okay, that is not very important right now, but we are going to use it just to define that L is going to be, theta dot is going to be L over mr squared. Okay, and taking the expression that we found for the energy, well, we are going to get that the energy is going to be m over 2 times r dot squared plus r squared theta dot squared, but that is L squared over m r, well, it would be m squared to the fourth plus b of r, okay? So we can cancel this r squared with this r to the 4 to get r squared here. And in the case of the isotropic harmonic oscillator, we will have that the total energy is going to be m over 2 times r dot squared plus l squared over m squared r squared, then plus 1/2 m omega squared r squared. So this is a very important step. We have found the total energy for the isotropic harmonic oscillator. So now what we want to do is what I mentioned at the beginning of the video. We are going to find a relation theta of r, okay, to be able to express the angle in terms of the magnitude of the vector r. Okay, so to do that, well, we see that in this expression, well, we need to add the potential energy of the particle that we are dealing with. Okay, so in this case we need to put the isotropic harmonic oscillator potential energy here and here, and then solve the integral to see, well, what are we going to get. So let me rewrite this expression with the potential energy of the isotropic harmonic oscillator. Okay, this will be the integral that we need to solve. As I mentioned, I just put the potential energy here. So first of all, what we are going to do, well, is just to multiply 2m into these brackets to get the integral of L dr over r squared, the square root of 2me minus m squared omega squared r squared minus L squared over r squared. Then we are going to take a common factor r squared from all this expression, and this is going to give us L dr, well, the integral of L dr r squared times the square root of r squared times 2me over r squared minus m squared omega squared minus L squared over r to the 4th. Okay, well, we can just take the square root of r squared because r is a positive quantity, and this is going to give us the integral of L dr over r cubed times the square root of 2me over r squared minus m squared omega squared minus L squared over r to the 4th. Okay. So what we are going to do now is to take the change of variable v equals 1 over r squared. So that means that r is going to be, will be to the negative 1/2. So the derivative of r with respect to b is going to be negative 1/2 b to the negative 3/2. Okay. Okay, and r cubed is going to be, well, b to the negative 3/2. Okay, so we are going to get that our integral is going to be L times dr, but that is negative 1/2 b to the negative 3/2 dv over v to the negative 3/2 times the square root of, well, 2me times 1 over r squared, but that is b, and then negative m squared omega squared minus L squared b squared. Looking that it is 1 over r to the 4th, that is b squared. Okay. So here we can cancel these b's. Okay. And we are going to get negative L over 2 times the integral of dv over the square root of 2mev minus m squared omega squared minus L squared v squared. Okay, so this is negative L over 2 times the integral of dv all over, and we are going to rewrite all this as the next. We are going to have the square root here times, of m squared E squared over L squared minus M squared omega squared minus LB minus ME over L squared. Okay, look that if we raise this to the second power, we are going to get this term here. This term, it is conserved, it is here. And look, if we multiply minus 2 times LBME over L, well, we are going to get this term here. And then plus this term squared will be cancelled with this term. So that means that everything I wrote here is equivalent to this expression that we have here. So there is no problem there. So what we are going to do now is to introduce a new change of variable. We are going to say that LB minus ME over L is going to be, let me write this with black, it will be the square root of M squared E squared over L squared minus M squared omega squared cosine of phi. Okay, so if we have that change of variable, well, we need to calculate dB. So that is going to be L dB is going to be equal to negative the square root of this times sine of phi. Okay, so look, in our integral, that is what we have here. We have L dV, so we can just put this to get that this is going to be the integral of the square root of this expression here times, and this is with respect to phi, this is sine phi d phi all over the square root of this minus, well, this thing squared. Okay, so that is going to give us this expression again times cosine squared of phi. Okay, look that we have a common factor here. That was the reason that we made this change of variable. Okay, so this is going to be equal to the integral of the square root of this times sine of phi. I'm going to do every step just to be sure it is everything correct. So again, this will be a common factor, and this will multiply 1 minus cosine squared of phi. So look, here we can cancel this term with this term, and well, the square root of 1 minus cosine squared of phi was, well, it is sine of phi, so it can be also cancelled with this. Just to get, and remember that, well, we had 1 over 2 here and here. So this is going to be 1 over 2 the integral of d phi, which is of course 1 over 2 phi. Okay, but remember that this was equal to plus minus theta 0. Okay, you may be wondering why I didn't add any integration constant here. It is because of this, because the integration constant is already theta 0. That was taken from an integral that is like this, theta 0 to theta of d theta. Okay, this is the origin of this expression here, plus minus. So the integration constant is already included in this theta 0. So this means that 1 over 2 phi is equal to plus minus theta 0. Okay, making that phi is equal to plus minus 2 times theta minus theta 0. But remember that phi was included in this change of variable over here. Okay, So we need to substitute what we just found for phi in this equation here. So if we have this, there is a cosine of phi here. Well, we get that L times B minus ME over L is equal to the square root of M squared E squared over L squared minus M squared omega squared. There is a squared here. Yes. Cosine of, well, 2 times theta minus theta 0. Remember that, well, if we take the negative and we plug it into a cosine, remember that cosine of negative x is equal to cosine of x, so this sign will disappear, okay? That's why I didn't put the plus minus here. Okay, and also remember that we made the change of variable b equals to 1 over r squared, so we can just take out this b to put L over r squared, okay? So if we work a little bit with this expression, first of all, we are going to get that L over r squared is going to be equal to ME over L, and then plus, and we are going to take this as a common factor in this square root to get the next. This is going to be the square root of, well, M squared E squared over L squared times 1 minus omega squared L squared over E squared. Okay, and this will multiply cosine of 2 times theta minus theta 0. Okay. Well, in this case, we can just take theta 0 to be equal to 0. And that will mean that if we are measuring the object, well, the motion of the object will start exactly at the x-axis, okay? This is r, so the object will start moving here in the x-axis, where theta is equal to 0. So we get that L over r squared is going to be m times E over L, and we are going to take the square root of this expression, okay, and look that it is the same as that we have here. So this is going to be a common factor to be, this is a 1 plus the square root of 1 minus omega squared L squared over E squared times cosine of 2 theta. Okay, and just to finish, well, we can just take this L, we can take it out from here to put it as L squared here. So we have accomplished our goal. This is the first important result of the video. What we can say about this expression is that it represents the, well, it is the equation of an ellipse that is, well, it is centered at the origin, okay? And, well, it is maybe not very familiar with the general representation of the equation of the ellipse, and that is because this is a polar representation, okay? We are not using x comma y, we are using r and theta. That is because, well, this is a polar representation, but in this polar representation, this is an ellipse equation, okay? So that means that the isotropic harmonic oscillator represents a motion that makes an ellipse as an orbit, okay? So that is, well, the first goal of the video. We just found some relation between r and theta, okay? So as we mentioned at the beginning of the video, we are also interested in finding a relation between r and t, which is the time, and that can be done, well, using this equation here and taking the potential energy that is according to the isotropic harmonic oscillator in this term here. So we are going to rewrite this integral in terms of that potential energy, and well, we are going to solve it to see what are we going to get. Okay, so now, as I mentioned, I put the expression for the potential energy inside the integral, and what we are going to do first is to multiply these two m inside the brackets to get the integral of dr all over the square root of 2e over m minus omega squared r squared minus l squared over m squared r squared. Okay, this is the first thing we get. The next step, well, we are going to take a common factor in this expression. It will be omega squared over r squared. Okay, we are going to factor that expression. And this is the integral of dr over the square root of omega squared over r squared times, well, 2e r squared over m omega squared. Then minus, it would be r to the fourth power minus l squared, okay, over m squared omega squared. Perfect. Okay, and it is very easy to see that we can cancel this square root with these squares, and this r is going to be here. Okay, so this is going to be the integral of r dr over omega times the square root of 2e r squared over m omega squared minus r to the fourth minus l squared over m squared omega squared. Okay, so what we are going to do now is, well, you can very easily notice that this process is very similar to what we have done first. So we are going to take u as r squared, okay? So that means that the u is going to be 2r dr at, if we make this change of variable on the integral, we are going to get the integral of, well, du over 2 omega times the square root of 2eu over m omega squared minus, it will be here u squared minus l squared over m squared omega squared. Okay, and here, well, we are going to do something similar to the other process. Here we are going to get du over 2 omega times the square root, and we are going to express this term as the next. It would be e squared over m squared omega to the fourth minus l squared over m squared omega squared minus u minus e over m omega squared to the second power. Okay, look that this term, it is conserved. Okay, and well, if we raise to the second power u, we get this. If we raise this to the second power, it will be cancelled with this term here. And if we multiply, then negative 2 times u e over m omega squared, well, we get this term that we have here. Okay, so this other way to express this is correct. And another thing that we are going to do is to make the change of variable u minus e over m omega squared is going to be equal to the square root of e squared over m squared omega to the fourth minus l squared over m squared omega squared times cosine of beta. This would be the new variable. And if we calculate du, it will be, well, negative the square root of e squared over m squared omega to the fourth minus l squared over m squared omega squared times sine of beta, d beta, of course. So our integral is going to be now, well, this whole thing. So it is negative the square root of this times sine beta d beta all over 2 omega times the square root of this expression minus, well, this thing that we have here raised to the second power, but that is this raised to the second power, which is equal to this raised to the second power. Okay, so we are going to write this. It will be this expression and then cosine squared beta. Okay, very similar to what we have done on the theta case. And this is equal to negative 1 over 2 omega times the integral of the square root of this expression times sine beta d beta all over the square root, again, of this expression here. And we're going to take it as a common factor. This will multiply 1 minus cosine squared beta. Okay, and as you can notice, this cancels with this. Sine beta cancels with this term here because this is sine beta. And we get that this is negative 1 over 2 omega of the integral of d beta. So this is again, well, minus beta over 2 omega. But remember that we mentioned at the beginning of this integral that this is equal to plus minus t0. So plus minus t minus t0 is going to be equal to negative beta over 2 omega. So beta is equal to, it would be minus plus 2 omega t minus t0. But again, remember that we are going to take this into a cosine, so the sign will not matter. Just to see it, let me remind you that we had, well, this change of variable, okay? And we just found beta, so we need to take all this okay, and replace beta with this expression here. So this will be 2 omega times t minus t0. Again, well, we can just take t0 to be equal to 0. That means that, well, the motion starts at the second 0. So this will be only 2 omega t. Okay? So remember that u was equal to r squared. That was our change of variable. And let me just write this. And, well, we can see here that, well, r squared is going to be equal to e over m omega squared plus the square root of, and again, we are going to take this as a common factor to get e squared over m squared omega to the fourth times 1 minus l squared over e squared omega squared here. Okay, and this multiplies cosine of 2 omega t. Again, we can take the square root of this expression here, and it's the same that we have here, so we are going to write it as a common factor. So we get that r squared is equal to e over m omega squared times 1 plus the square root of 1 minus l squared omega squared over e squared times cosine of 2 omega t. In this case, what is very interesting to notice from this expression is that it's a periodic function, okay? And look that this cosine is, well, it has a 2 on its argument. So that means that on a period, well, it will go to the maximum and the minimum twice. So that means that the period of this, well, is going to be 2 pi over omega. Okay, so this would be the relation between r and t. Okay, so in this case we are able to find what is the distance between the origin and the object that is moving. We saw that is moving on an ellipse. Okay, so what is the relation between the distance from the origin to the object with the time-dependent relation? Okay, so yeah, that is what we have found here in this function, in this expression. So that this will be the second important result of the video. Okay, the relation r of t. Another interesting thing that we can mention about this result is that if you remember the solution of the Kepler problem that we have been dealing with in previous videos of the channel, we saw that the period of the Kepler problem depends on the major semi-axis of the ellipse of the motion. Okay, well, it depends on the major semi-axis. In this case, it doesn't depend on that. In this case, the period is actually a constant. Okay, so that will be a very interesting difference between the isotropic harmonic oscillator and, well, a planet that is moving around the sun.